Because we've got a couple of pieces. That's why they're called piecewise functions.
Wait, so then, okay, for this one,
yep.
We make that little table, right?
Yep.
Okay, I thought so.
So I'm going to do a purple table for the top one, and I'll do a green table for the other one. I pick my x's to find my y's. Whoop. So what the squiggle means just means I'm going to pick my equation to be y equals 1/2 x, but only when my x's meet this rule. So what x's should we use? For the purple one. Is 1 less than or equal to 0? What numbers are less than or equal to 0? 0. All right, guys. -1. -2. You can do -3, -4, -6. When we substitute that 0 in, oop, not the button. Because my x's need to be less than or equal to 0. When I substitute these into my equation, my y equals 1/2 x. I'm going to put that 0 in place of this x. So 1/2 times 0 is 0. 1/2 times -1. -1/2. 1/2 times -2. -1. And I could keep going. That gives me 3 points. That's enough to at least get the vibe going on here. This first point we do need to pay attention to. Are we going to be using an open circle or a closed circle on this point? Closed circle, because we have this equals to under here. So I'm going to draw it just like a normal point at 0, 0, -1, -1/2, -2, -1. I could do -3 and get -1/2. I could do -4 and get -2. I could keep going. Could I keep going forever and ever and ever and ever and ever? Yeah. So when we draw this, I for sure need an arrow on this side. So connect them up using a ruler. There's rulers out on the table. Nope, I'm supposed to use a pen. Could I keep going to the right? No, because my x's need to be less than or equal to 0. So we're only having the one arrow on it. We're going to do the same thing for the green one. I have a green up here. Our function rule tells me that my y equals 3 minus x, but only when I pick my x's to be greater than 0. So what x's do we want to pick to help us find our y values? 1, 2, 3. We're missing one important piece. 0. Even though it says greater than, I still need to know what happens at 0, because what if my x was 0.001? I could have that. That's greater than 0. So I need to know what happens at 0, even if 0 is not included. So what is a way that I could draw that point and show that I can get real close to 0, but I can't actually touch it? Open circle. So this one we're going to graph with an open circle. So then let's find our y values. When x is 0, what's my y on the green equation? 3 minus 0. 3. 3 minus 0 is just 3. What about 3 minus 1? 2. I know I have such hard questions today. 3 minus 2. 1. And 3 minus 3? 0. So we've got a really good kind of view of what's happening here. So at 0, 3, we are putting an open circle. Then we're going to have our 1, 2, 2, 1, 3, 0. Did I stop because my function rule told me to stop, or did I stop because I was running out of graph paper? Did we have to stop when x was 3? Nah, I could keep going. We stopped because we got lazy and didn't want to draw more on the table. So could I put an arrow on this side?
Yeah.
Yeah. Can I put an arrow on the left side?
No.
No. So when we connect it, it's going to look like that. Correct. Since it's only if it's in between the y, if this was an inequality, that's when we do our dotted and dashed kind of stuff. Because we're just looking at these points. These are linear equations. They just have a domain restriction is what that piece is. Well, I'll write you past, but we're going to get started anyway. Okay, questions on this one? Okay, so we're going to continue working with these piecewise functions, but we're going to do a very special kind of piecewise function that is called a stepwise function. Yeah. So I'm going to give us a definition for it here. So grab your notebook now. We are doing notes on this.
Under pressure. No, I wasn't. Did you study? Yes, I was going to do it. Yeah, okay.
Take your shirt off.
Our teacher didn't tell us how to do it. Our school was so that's why we become the line. I was going to say, so we had the menu. I knew how to like put it in. I just know how. It took me forever. But I was the only person in my class that actually learned. They wasn't listening.
All right. So we're going to be working with things called stepwise functions, which are a special kind of piecewise function. So I'm going to give us our proper definition first. A stepwise function is a type of linear piecewise functions So it's a piecewise function made up of only lines. Piecewise functions don't have to just be lines, but since that's all we know right now, that's all we've been graphing so far. So it's a type of linear piecewise function with a graph that is a series of horizontal lines or segments. Usually segments, but it could be lines. Which you have interacted with. Guaranteed 100%. If you have gone downtown ever. Even if you weren't the one driving. You've seen it. Because this is how parking garages do their pay structure. This is how parking meters will do their pay structure. This is sometimes how, like some of the bougie movie theaters where you pay like a flat rate for a certain amount of time to go in, or arcades will do this. So what it is, it's made up of horizontal line segments. So I'm going to talk us through one before we get into proper graphing. I'm just going to think it through out loud and kind of put a little sketch up here. So if I go down to Circle Center Mall and I pull into the World of Wonders garage, the big one that has like 6 layers or like 10 layers. And if I pull in, I decide, oh, never mind, I really don't want to get out of my car and walk that far to the mall. And I just go and leave. I have to pay the parking, right? I still have to pay for it even though I drove in and I'm driving right back out. So going there for 0 minutes, I'm still paying whatever the $5 is. I just pull in, change my mind, and leave. If I stay for 2 hours, I'm still paying that $5 because the window is usually from 0 to 2 hours. So no matter if I am there for 30 seconds or 2 hours, I'm paying the $5 or whatever the fee is. The second it jumps over 2 hours, 2 hours and 1 minute, I'm now paying the next rate. That's usually up to like $10. So it'll jump and teleport up here to just over 2 hours. So 2 hours and 2 seconds. They may charge me $10 now. And it'll stay that same rate until we get to maybe 4 total hours. And then again, it'll jump and it'll teleport up to maybe $15 because they want to get your money again. So the longer you stay in the parking garage, the more it's going to cost you because maybe this one goes to 6 hours. So these are what a stepwise function looks like. It is literally made of horizontal segments, little steps. It looks like stairs. They might not always be good stairs. Sometimes they're like real jumpy when we're looking at them. So they don't have to just go step and increase each piece. They can be any place all over, as long as they look at like kind of one of those AI marble tracks where they're singing the song and hitting the xylophone things. I love these things. They're so satisfying. Okay, but that's what the stepwise functions look like. And we're going to practice working with them. These are a thing that happens in real life. Like I said, these are how parking garages work. This is how entrances at like arcades usually work. This is how postage stamps work. All that kind of stuff, which is honestly how we're going to start this. Open your postage stamps. Okay, so we're going to do 2 stepwise graphs. And I'm going to give you a table and a graph and a regular graph. So this is 2 problems and it looks like 3 things. So the first one, the table and the graph go together. I'm giving you both so you don't have to try and draw them in. I'm trying to make them easy to read and easy to see. So I didn't want us to have to spread through it. So this is from the textbook, so I believe the stamp information is slightly out of date. I do not believe it's 47 cents anymore for a single stamp. Somewhere around there. But we get the same kind of value. What's up? I'm good at counting. And these things totally get like a super stat in between. So they're good.
Open the door. Oh, the name. Oh, I'm good. Did you guys give me that the first time?
No, I'm gonna run.
I told the name to go open the door.
Thanks. I was gonna say they static together and then they stick together, and so I can't. I appreciate y'all not leaving it later. All right. So we are looking here at the cost of mailing a letter is set by the Postal Service. So this is what the pricing scale used to look like. They pulled real data. I think they pulled this real data about 6 years ago, maybe 10 years ago. So it was real data. I think it's a little out of date, but it was real data. Y'all, it's messed up. We don't need to fight over my scissors and glue sticks. And what we're going to do is we're going to graph this up. So this is the table and the graph. Those things go together. The regular graph we will do on the next one. What's up?
Can I have the graph from Friday? No.
Huh?
The graph from Friday?
trying to remember what we did on Friday. Oh, it was some of these. It was just 2 regular graphs.
So what's the one?
2 regular graphs.
I'll tell you after we're done. Thank you.
That way. We should, if we can get through this.
Okay, so let's go through this. So
We should. We should have time. All right. So when we give you a table like this, we don't have to make like the little C tables. You can. You absolutely can. But we have enough information here that we don't have to make like a T table and fill in values and find something in between. What we have in this table is it lists our endpoints for us. My x's start at 0 and they go up to 1 ounce, meaning at 0. I could take an empty envelope, fill it full of hopes and wishes and dreams, and mail off my empty envelope. It weighs almost nothing. But would they charge me just for sending the wishes and dreams? If I did not put them in an envelope, if I just thought really hard and sent you wishes and dreams and good thoughts, will the post office charge me money if it weighs nothing? Like there's nothing physical for me to send. No paper, no nothing.
Yeah.
Post office gonna charge me to send nothing?
No. Wait.
Looking at this piece here. If I try and mail something that literally has no mass, that is a nothing. I walk in and say, here, can you mail these kind thoughts? Post office lady is gonna look at me like I'm a little bit nuts. But is she gonna charge me money? If I just bring my good thoughts and put them on the counter? No, because there's nothing there. So if I can mail something that almost weighs nothing, but I can't send something that weighs absolutely 0, how can I mark that down? What are we going to put on that end? If I have a less than, how can I mark that on a graph? Thinking about the less than. How do we mark that for a specific point that it could be real close to 0? I could send an empty envelope. But I could not send no envelope. Like I can't send nothing. So we're going to do an open circle on an end that has a less than. I could take my envelope, get out the kitchen scale, and fill it full of glitter. Chaos. I could be very specific and get it exactly to 1.000000. And they're going to make me pay 47 cents for it. If I put an empty envelope that just has those good thoughts, nothing else in it, they're still going to charge me 47 cents. Or I could fill it absolutely full of glitter, cause a little chaos, and still be charged that 47 cents. So anything between 0 and 1 ounce costs that 47 cents. So the way we put that on the graph is we're going to find our 0 ounces at 47 cents, so just below this 1/2 here. We put an open circle on the 0, because I cannot mail good thoughts and wishes, but I could mail an empty envelope if I was feeling like it. And I could also get my kitchen scale out and get exactly to 1.000 and still have it cost 47 cents. Taking our little individual glitters until it says 1.000. Mailing glitter and cause chaos. Those two pieces, when connected together, are my first segment. Because 0 is less than my x, which is less than or equal to 1. X is between 0 and 1. So it gives us my endpoints of my segment there. 0 and 1 are my endpoints. 0 has an open circle, 1 has a closed circle, and they're at 0.47. I'm going to do each of these segments a different color. If you guys ever would like colors, I have so many colored pencils and markers. I'm happy to loan them to you guys. So if you ever need colors, please let me know. I have tons. So as soon as I have my envelope full of glitter, and I put too many glitters in them, and it goes 1.001, how much will I be charged? As soon as I'm just a hair over 1. 0.68, it jumps. We have a teleport situation here. So it's going to jump up to our 0.68. And that's as soon as it hits anything over 1. So it's going to be somewhere up here. If it exactly equals 1, it's down on the green line. But as soon as it pops up over 1, it jumps up to where that purple circle is. It'll stop costing me 68 cents when I get to 2 ounces. So if it hits exactly 2, so now in my envelope full of glitter, I'm also putting a candy bar. Candy bars and glitter. And I can get that to be exactly 2 ounces. 2.000. It's still going to cost me 68 cents. So anything, what's up?
For the purple one, the first one,
The first dot is where it jumps up to 1. So that's my open circle when x is just greater than 1. It could be 1.0000001 ounces, and they're going to charge me the 68 cents. What's that? Okay.
I don't understand what's going on. I'm being honest. Like,
More. Give me a little more.
it's like the graph,
Mm-hmm.
that table thing. I don't know.
So the table is information we give you. Like, you don't have to fill in the table. We're just trying to plot that up. So if x is between 1 and 2, it costs me 68.68. So you could just start by putting a dot at 1, comma 68, 2, comma 68. Connect them up. We just need to pay attention to the fact that I can't equal 1 on this segment. I can get real close, but I cannot equal it. If it is between 1 and 2, they're going to charge me my 0.68. If it is between 0 and 1, they're going to charge me 47 cents. So if I have an empty envelope, I'm just sending good thoughts, it's going to cost me 47 cents. If I have an envelope that is 1.0000000, like we are, as far as our scale will go, at 1, full of glitter, they're still going to charge me 47 cents. As soon as I put 2 extra glitters in there and it's 1.00001, now it jumps. It teleports up to 68 cents. Just those 3 extra little glitter pieces pop me up over into the next price bracket.
Well,
We're good. Let's look at another one. Let's look at another one. Sometimes it takes a few to get through and see what's going on. So if my x's are between 2 and 3, on the low end we have a 2, on the high end we have a 3. It's going to cost me 89 cents. So the second my envelope with candy bars and glitter goes over 2 ounces, 2.00001 ounces, what's it going to cost me? 89 cents. So the second I am a molecule over 2 ounces, it's going to cost me 89 cents. So I have to put an open circle at 2 and 89 cents, which is going to be somewhere around here-ish. You okay on that part?
okay.
So that's my open circle from here. So then we're going to find the right-hand side. If I get to exactly 3, my scale says 3. Oh. Nothing extra. I got it exactly at 3 ounces. What's it going to cost me?
$1.
If I am exactly at 3.
89 cents.
89 cents. Whether I am just barely over 2 or exactly at 3, it's still going to cost me that 89 cents.
Wait, I'm understanding.
Will there be like a time to try to get rid of
I'm trying to go.
It would be that we would just give you like an ordered pair then. because here it says my x has to be between these two values. 2 is less than x, which is less than 3. So x is between them. So that means it could be anything in between them. I could have 2.01, I could have 2.5, I could have 2.8. Everything in here is a point that it could be. So we connect those all up. And if you want to do points in between, you absolutely can. You do not have to, but you absolutely could. Okay? A little better?
Yeah, I'm understanding now.
Cool. One more piece on this one. And then we're going to do domain and range. All right, so now I have from 3 to 3.54. Which feels like a weird unit. I believe it's because it makes it kilogram, 2 kilograms, something like that. Makes something weird metric-y. It's going to be at $1.10. So the second we get over 3 ounces, it jumps again. All the way up over $1 here. So 3 and $1.10 gets an open circle. And then our right hand end of this is at 3.54, just a touch past 3.5. And it's still costing us $1.10. At that point is where I believe the post office says, okay, you're not a letter anymore, that's a package. You've got way too many things out of an envelope to count it as a letter anymore, because this is just for letters. I believe over 3.54 ounces is when it classifies as a small package. Okay, we see that graph-wise, what's going on? Is that okay? All right, so now I'm going to ask you the hard question. What's our domain? What is the smallest my x's can be? 0. So we see that in our green line, right? So where does my green line stop going to the right? 1. Does another line start at 1? Yeah, it just jumps up to purple, right? So I have a value at 0.9, I have a value at 1, and I have a value at 1.1. Like, there's no breaks in between. It jumps, but there's not a break in between. So it starts at 0, I can go past 1, it still keeps going. Where does the purple line stop? 2. Does the whole function have a break there, or does it jump somewhere else? I have my 1.9 on the purple line. I have 2 on the purple line. Do I have 2.1 somewhere? If my x is 2.1. Does my function stop at 2? I mean, no, it just jumps up here, right? So I have 1.9, I have 2, I have 2.1. There's no place where it gaps. It just starts up here. Where does this whole graph stop going to the right? At 3.54. So this goes from 0 to 3.54. When we're putting these into our interval notation with the parentheses and the brackets. Parentheses means I cannot touch it. Bracket means I can. So the 0, can I touch it, or is that a lava pit?
It's a lava pit.
It's a lava pit. It's a hole, right? I cannot exactly equal it. That is a gaping hole. I have to jump over it, or it's a lava pit. I cannot touch it. I will burn my finger off. We cannot touch, because it has this less than here. So if we cannot touch it, We think of it, it's like an infinity, means we cannot touch it, so we put a parenthesis. How about the 3.54? Can I touch that one?
Yes.
Yes, because we have a closed circle. If I can touch it, we put a square bracket.
Wait, are we moving the biggest and the highest or something?
Yeah, this is
I mean, the biggest
left,
and the
leftist and
largest.
rightist, because it's domain.
Oh. Okay.
So as far left as we can go, as far right as we can go, and there's no gaps in the middle. There's no breaks. How about our range? What y values do we have? 0.47, and it's stuck there for a hot minute, and then 1.1, and where else do we have y values? 0.68 and 0.89. It's never in between. It's not the interval from 0.47 to 1.1 because it never exactly equals 0.5. It never exactly equals 75 cents, 0.75. It never exactly equals 90 cents. So it's not everything in between 0.47 and 110. It is exactly the values. So we put the squiggle bracket of our 0.47 and our 0.68 and our 0.89 and our 110. So when we're looking at our range, we're just listing out the values. It's like a discrete set. Questions on this one? We are still going to do the other one. I've got 7 minutes. This is our next one.
No, put it back in.
It's another piecewise, but it's also a step function. You can approach these exactly the same way we did the piecewise and the bell work. Make your 3 T-tables. I've got 3 pieces here. We're just picking our pieces. So I'm going to just pick my 3 pieces here. When we have this big squiggle bracket, this means f of x is the same thing as y equals -2, but only when I pick my x's to follow that rule. What x's will we pick? -1, 0, -2, and we could do more, -3, -4. If x is 0, what's my y here? -2. If x is -1, what's my y? -2. If x is -2, what's my y? -2. So we have the points 0, -2, -1, -2, -2, -2, and I could keep going. -3, -4, -5, -6, -7, -10, -100, -1,000,000. Those all fit. So this keeps going straight to the side. Because my x's can be less than or equal to 0. Let's look at this middle one here. Again, you could make yourself a T-table. Totally fine. Or we can notice that my x is between 1 and 3. And what's my y value going to be for both 1 and 3? 4. So when x is 1, I have a point at 4. Since it's an equals 2, I'm doing a closed circle. When x is 3, I have a point at 4. Again, there's an equals 2, so I'm doing a closed circle. And it's true for every x in between them. So we're going to connect them up. Again, you can absolutely make a table for these. Totally fine. But we'll also start to hopefully see the patterns here. Our last one here, what's this one going to look like? Where am I going to start? What's up? Yep. Green one would look like, what x values would we pick for green? We need to start at 1, and we need to end by 3. So we could do one in the middle. Our equation is y equals 4. So if x is 1, my y is 4. If x was 2, my y was 4. And if x is 3, my y is 4. So very similarly for our last one here, if I need my x's to be greater than or equal to 4, what x's are we going to pick? 4 and 5 and 6. My equation says y equals 1 for these x's. So what's my y value when x is 4? 1. What's my y value when x is 5? What's my y value when x is 6? 1. So we get points that look like this. Did I stop because my function rule told me to, or did I stop because I ran out of graph paper? Because I ran out of graph paper. So I can connect these up, and this will keep going. We have 2 minutes left, so I'm going to give you a thought about this. When we look at domain and range on these, since there's a gap in between, it stops at 0 and it starts again at 1, we're going to do separate domain pieces for each segment. So we'd write purple's domain, negative infinity to 0. Close that one off. We'd write green's domain from 1 to 3. Close it off. 4 to infinity. So it would have 3 separate pieces. So that took us a while. Sorry. But that was all we needed to do today. Homework 1-6. We're still going to talk about what's on it tomorrow. If you do not pick it up on Friday, I have those right here. Feel free to pick that up on your way out. We're going to talk about the other kind of